Yeah, maybe it's okay to get started since we're on tight time today.
Yeah. Okay. So welcome everyone. So today we're very happy to have Michele Coscia, or Coscia, I don't know how to pronounce it, from ITU in Copenhagen. And so Michele will talk about leveraging rich node data analysis for cultural analytics. So Michele, if you can take it away.
Thank you. I hope you can all hear me well. Thank you for inviting me. It's an honor, and I'm very happy to discuss about these topics, which I find very interesting. So as you can see from the title today, we are going to look at networks with rich node attributes, and specifically on the focus on what we can use this structure for cultural analytics. So let's get started. So what I'm going to talk about is the scenario where we have a bunch of things. The first thing that we have is a network, of course, otherwise that would be weird to be in a network seminar talking about these kind of things. But the other important ingredient is having lots of node attributes that are very specific type of node attributes. And I'm going to use the first part of this presentation to discuss about what I mean by these rich node attributes. And the question is, how can we make sense of these node attributes? So the focus today is not so much on the network itself, but on how the network can help us making sense of the node attributes. So the focus is really on the node attributes, not necessarily on the network itself. So I don't really have to talk too much about why we think networks are cool. I think everybody here is on board with that, but a very brief introduction about this. So networks, the things that fascinate me about networks is that the first thing that they do is to enlighten. The structure of the network is usually very informative and allows us to say very interesting things about a particular phenomenon. You don't know what the networks on the slide represents, but you can already see this network and see that it has an interesting structure with some pretty evident clusters and some other areas with lots of triangles, lots of nodes with low degree, and so on. So it just creates a map that gives us an idea of what is the phenomenon that we are looking at. So analyzing the structure of a network is very interesting. But what I think is even more interesting is the fact that things happen on a networks. So we can run processes on them. The classical one that lots of people think is spreading of some sort of event, like a disease or misinformation or information in general on a social network. And we do these things on networks because we think that the network structure matters. So we think that the topology of the network, how the edges are distributed among the nodes, will greatly influence how these processes happen in the real world. So that we cannot assume that everything happens on a Euclidean space. And so this is the key that underlies all the methodologies that I'm going to briefly talk about today. So just to give you a roadmap of the things that we are going to look at, the topics, I'm going to take inspiration from 3 papers that I wrote last year. The first one is about collaboration between musicians in Italian music. Another one is genetic relationships that have been inferred from archaeological data. And then we are going to have a little bit more a classical example on political opinions on social networks. So a classical polarization study. So I think that's one of the things that I want to underline, because I feel is the part that conceptually is the hardest when doing the kind of things that I do, is understanding the relationship of the things that we want to analyze. So normally, at the very least, when I look at the majority of the paper in network science that I read, I can see that there is some sort of identity between the node and its attributes. So we think that they are kind of like the same thing. Like attributes are merely specifying qualities of the nodes. So you say, okay, we have a node, it's a person in a social network, and their attributes could be their political opinion, their how much they write on social media, and so on and so forth. So ultimately, what we want to do is to say something about the nodes. So that's what I think a lot of network science is. We want to say something about the nodes. We want to say something about how the nodes related to each other in the structure as a whole. But what I do instead, and I try to also give you the ideas during the introduction of the talk, is that this equality does not always hold. There are some very interesting things that you can do when nodes and attributes are actually fundamentally different things. So they're not the same entity, they're not the same thing. The attributes are not merely specifying some qualities of the nodes, and the attributes themselves can be the unit of analysis that we want to look at. So how does this translate into the cultural analytic example that I gave you before? Well, for instance, one of the things that you can do is that you want to estimate the distance between two attributes. So you have two node attributes that are distributed in this network in a different way, and you want to figure out how close they are to each other using the network structure to base your answer on. So it's not an Euclidean distance, it's an Euclidean distance that is measured on the graph. You can also say, okay, how about we have a single attribute and we want to know how much it concentrates into the network structure. You can also do that. And this is actually a technique that Renault has developed. So not everything that is in talk is actually stuff that I developed. I also take something from Renault. We can also learn attribute classes. This is like a direct application of knowing the distance between two attributes, because if you have lots and lots of attributes and you can calculate the pairwise distances between all of them, then you can do clustering. So you can do clustering of node attributes, not of nodes, which is what you will normally do when you do community discovery. And you can do the same thing when you have time information. So you can find temporal clusters if the node attributes represent moments in time. You can do more things than that, but this is what I decided to focus on for the talk today. So again, let's see how does this thing translate into cultural analytics. So we start with calculating the distance between two node attributes. And here I'm going to use the polarization example. So here we have a social network where the nodes are the people and the connections are the social relationships. So the one that you see plotted in the slide is a very classical network that you get from former Twitter, where you have accounts that are mentioning, replying, commenting on each other. Now, the attributes of these nodes are their ideological score. You can imagine them as sort of answers to the question, how liberal are you? Or how conservative are you? So here you can see that there is a pretty clear distinction between two very evident clusters of lots of people that are on the liberal spectrum that are blue, and lots of people that are on the conservative spectrum that are red. So the question now is that we want to say something meaningful about the ideologies, not necessarily about the people. The people by themselves are not super interesting. What is interesting is that are the people who hold different ideology interacting with each other or self-separating? It's pretty clear from the picture they are self-separating, but by how much? If I show you two different networks that look a little bit the same, can you tell whether one is more polarized than the other? In the sense that the ideology of like the liberal ideology is farther away from the conservative ideology. And the important thing is that ideologies are not people. So attributes are not nodes. That's what I meant, right? We want to talk about ideologies. We don't want to talk about people. We want to talk about the node attributes. We don't want to talk about the nodes. So the distance between these ideologies through the people opinions is interesting because here the networks mediates the opinion and their dynamics, right? There is the whole discourse about the echo chambers. If the two ideologies are intermingled, then that means that we don't live in an echo chamber. So if people with one specific ideological score interact with people with other ideological score, we think that polarization is low. And if they don't do it, we think polarization is high. This is something interpretable, something that has consequences in the real world. So one thing that you can do is that you can say, okay, well, we want to understand what's the distance between fundamentally what there are two vectors, right? And we know how to do it. We know the Euclidean distance, which is the straight line distance. Very easy. Now I write the Euclidean distance, and I don't know if you can see my pointer, but here is the formula that you can see there. It looks a little bit weird because you normally would not write the Euclidean distance that way. There is multiplication with the identity matrix that does nothing in the Euclidean distance. But once you understand, once you can write the Euclidean distance in this way, you understand that that matrix is actually not doing nothing. It's determining the shape of the space in which the two vector lives and how you should weigh each pair of dimensions in this space. In the Euclidean case, all dimensions are equal because moving one step forward is the same as moving one step to the left. But for instance, you can do more complex and interesting things. So you can have the Mahalanobis distance, where you understand that these two vectors may be correlated, and so you may take the covariance into account of these two vectors in order to decide that these spaces, some directions are more important than the others. So if you're moving along the correlation line, you're actually moving less than if you move against the correlation line, if you want to calculate the distance between 2 points. And once you do this trick, then you can realize, okay, maybe we can put the graph structure into this. And this is what I do when I do the generalized Euclidean distance, which I use the pseudo-inverse of the Laplacian, which gives us an idea of how things propagate through the graph. And it gives us a proper metric in which these two vectors, P and Q, now become node attributes on this network. And then their distance takes the network structure into account. So basically what happens here is that we add a network, and the nodes of the network now are kind of like demoted, if you may, to be the axis. So the nodes of the network determine the space in which things happen, but they're not necessarily the most important thing. The most important things are the node attributes. So at this point, you can see that each point that you see is actually part of this table of node attributes. So the nodes are the dimension of analysis, but the node attributes are the real observations. So this gives us a very nice measure of ideological polarization in a society or in elites, because it can be interpreted as this number that we calculate is the literal distance between two ideologies on a social network. How much the people who hold these ideologies are interacting with each other or not interacting with each other. We made a bunch of case study. I think this is the easiest one to understand. We connected congressmen into the US Congress, depending on their voting behavior. So how much they vote the same when there is a bill proposed on the floor. And these congressmen also have some ideological score that are gathered again through their voting behavior. And you can see that as we go left to right, time flows from the 81st to the 116th Congress. And we can see in the network structure that they get more and more separated. So it's a sign that things are getting more polarized. The histogram that you see is also the distribution of the values of the node attributes, just the values themselves. And then in the very bottom, you have this generalized Euclidean measure that tells us on the network the distance between the red and the blue ideologies. And we can see that indeed it was pretty flat for most of the time, but then it starts increasing and reaches values that are higher in modern times. So we actually give some substance to this idea that there is this increase in polarization in the US Congress. Another thing that can be done, and now we are switching gears to to a different topic. Now we are talking about archaeology. So when we talk about archaeology, we're talking about a different type of network. Here we are talking about a material culture network. The idea here is that we have a lot of buildings in a Neolithic village, and inside this building, we find different artifacts. And if we find the same type of artifact in two different buildings, we can connect them in a network. We can say, okay, each building is a node in this network, and each edge represent the amounts of material culture or shared material culture that these two buildings are have in common. And we only take into account connections that are statistically significant. So in here, in this visualization, we have that the node size is the number of artifacts that we find in that specific building. The edge size is the number of shared artifacts between two buildings, and the edge color, the significance of the connections. Now, in this specific village that we are talking about, it's called Çatalhöyük, is in Anatolia in Turkey. The specific culture also buried people inside the foundations of new buildings. So when they were erecting a new building, they were on the foundation of this new building, they were burying people. It was part of their culture. And we can sequence the DNA of these people, and we can figure out who was related to whom. So now we have a very interesting thing, because we can estimate first, second, or third degree biological relationships. So we know who was related to whom. This adds some very interesting node attributes on this network, because for each group of family, we can see how it spreads on this network of material culture. So in this particular case, we have that 15 people were buried on this specific family, which is first, second, or third degree relationship. So first degree means siblings or parent-child relationship. Second degree is cousin. Second degree is like aunt and uncles, and third degree is cousins. So in this particular family, we have 15 people buried in building B1, another bunch of people in building 50, building 3, and so on. And the ones in white are the ones that don't have any member of that family. And now we can ask ourselves a question. Is this distribution random? Because if we are able to say that this distribution is not random, we are actually saying something interesting about how material culture relates to genetic relatedness, because these buildings are connected because they share material culture. So if these families are buried concentrated in this network, it means that people were not buried randomly, they were buried, or to be better say, material culture is not distributed randomly. Material culture seems to be shared between buildings that also showed this kind of biological relationship. But again, in order to answer that question, we need to calculate how concentrated in a network this attribute is. And so what we can do this with this network variance measure, which I don't have a slide because this is the methodology that was developed by Renault. And once you have this value, you can say, okay, well, is this value that we are observing, is this significantly higher or lower than we would expect randomly? So we generate a bunch of null models, or we generate a bunch of null family that has the same number of members and the same relative distribution, but they are scattered randomly in this network. And we can see that actually the network variance values that we see from the observed network are significantly lower than what we will see from the null models, which means that these families are concentrating much more than you would expect, given the size of the family, which prompt us to conclude that yes, indeed, there should be a relationship between material culture and biological relationship, which is a big deal in archaeology, because it tells us that when you don't have biological information, because you don't have the burials in the buildings, you can still argue that buildings that have shared material culture probably have some sort of biological relationship or social network relationship. A third class of things that can be done is to learn attribute clustering, attribute classes. What we are trying to do here is to fundamentally perform data clustering between node attributes. And for data clustering, we need a distance function because each data point, we need to know how far each data point is from all other data points. And we just did it, right? When we did the polarization example, we just say, okay, we have two attributes, we calculate the distance between them. So what happens if we calculate systematically these distances between a large number of node attributes on the same network? If we do, we can actually use this information to find clusters of node attributes rather than clusters of nodes, as you will do in community discovery. So the kick here is that this generalized Euclidean distance that I explained to you at the beginning, or like in the first case study, actually doesn't work that well. So here there is a little bit of information dense plot, but the key thing here is that the generalized Euclidean distance is this blue line that you hope you can see in the plot. Now I circled them with these red boxes, and it basically performs pretty poorly. It performs as well as the baseline, and in this case, the baseline is actually the straight Euclidean distance. So by itself, the generalized Euclidean distance didn't work very well, but it did work very well, and now I'll highlight with the red arrows, when I combine this in a larger framework. For, in this case, I use TSNE, which is like this dimensionality reduction technique. TSNE also needs a distance function to understand how to reduce the dimensionality. And when I give the generalized Euclidean to TSNE, and then I use that to find the clusters, this works really, really well. Top performance in several data sets, and in some cases, it requires some additional step doing some noise reduction. So the plots here that you're saying, maybe I should have described them first, are from 3 different data sets where I have a ground truth about the real label classes of some data, and then I calculate the mutual information, the adjusted mutual information between those ground truth classes and the one that I get from the clustering when I run using the generalized Euclidean. So I compare with a bunch of different methods that create node embeddings in different ways, but they do not have this generalized Euclidean distance as their base of function. And I can see that combining usually generalized Euclidean with TSNE creates the highest adjusted mutual information, which means that the clusters are of a higher quality and are able of recovering the ground truth more easily. Okay, so can we do this? Okay, so what we are doing here is that we are calculating this pairwise network distance between attributes. We use these distances to give TSNE the shape of the space on which TSNE is going to do the dimensionality reduction. And then we use these embeddings that we get from TSNE on a classical clustering algorithm. You can use dbScan, you can use k-means, because the hard part has been done by doing this network-aware embedding using TSNE. And so you can learn attribute classes because normally you're going to see that attributes do not spread randomly in this network. The network structure will influence how these node attributes spread. So in this particular case study, we are going to look at the music collaboration network. In this network, every node is a band, a music band, and the bands are connected if they share members over time. So if a same person plays in 2 different bands, then we connect these 2 bands. And again, we do this with a statistical significance test. And then we can superimpose the genres that these bands play as the node attributes. So for instance, what you're seeing right now, I hope the slide is clear enough on the projector, is heavy metal, how heavy metal distributes in this network. And by the way, these networks is only using Italian bands. So this is a picture of the Italian music industry. So here you can see where in this network are the bands that publish records that are classified under heavy metal. But you can look at hip hop, which is like this more central cluster, much more tightly packed. You can have Neapolitan songs, which are in a completely different part of the network. You can see that the part of the network in Neapolitan song is very different from hip hop or heavy metal. Jazz is spread out in the network. Then you have house, which is like this electronic type of music. So all of this music, and now I'm gonna flip back and forth between them, are in different part of the network. And then you can find meaningful ways of saying, okay, well, some of these genre pairs are gonna be closer to each other than other genre pairs. So when we do this systematical estimation of distances between these node attributes, we can reconstruct this structure of how the various clusters look like. We do this very classical agglomerative clustering where we merge the closest two pair of node attributes, and then we recursively do that until we merged everything together, and we get this nice distance matrix. And the blocks in the diagonal are the clusters, a low-level cluster or macro clusters that you can find. And you can see that whatever ends up into these blocks on the diagonal is meaningful. And here, bear in mind that bright means very similar. So if you see a dark band, it means that these genres are very different, but a very bright patch means they are very similar. So the first genre on the top left is basically different types of heavy metal, which makes sense. That will be more or less in the same part of the network. Then you have another block, for instance, various types of different hip hop genres. Then you can have the things that Neapolitan songs will cluster together with, different other type of world music. And you can see here that also nearby blocks also have some sort of relationship with each other. So before we had this like world music, mambo, samba, tango, and you can see that jazz, swing, Schlager, there are a different cluster, but they are part of the same overarching structure. So if we go up in the level of the hierarchy, this will also make sense to merge them together. And then in a completely different part of the network that is separated from the rest by a very dark bands, so very, very dark, very unlike genres, you will find electronics, which is its own thing. And it doesn't collaborate too much with other genre. And you can find different types of house and dance music. So if we want to find temporal cluster, so we want to talk about the evolution of node attributes, for instance, in a network, we can do the exact same thing that we just did. So we still do clustering, but we can do it with time. So the idea here is that we need to adapt a little bit the technique that we use to create the clusters, but overall, we are doing sort of like the same thing. Here, what we are doing, and we are still in the music network, we are going to say, okay, now the node attributes is not the music genre anymore, it's the year. So it is a count of how much active this band was in a specific year. So now the networks are a little bit small, so you're not going to be able to appreciate the differences, but we're going to have a particular version of the network. The network is the same, the topology is the same, but the node attributes will say, okay, how many albums, let's say, these bands put out in 1984 and how many albums they put out in 1985. So we can calculate the distance between consecutive years, still the network distance with the generalized Euclidean measure, calculate this distance between consecutive years, and then we will merge them. So we're going to say, okay, well, let's say the 1984 and 1985 were very similar. So these are the most two similar years, let's say. So we merge them together and we create a new node attributes that is the combination of all the activity in both years. And then we can repeat, we can say, okay, how much is this cluster far away from 1983 or far away from 1986? And if it's very similar, we're going to keep merging them. And we keep merging them until we can create an overall structure that, in a sense, shows us when were the periods in Italian music where things were relatively stable and when there were the periods when there were particular changes. So this kind of structure, this kind of cluster that put together all the years means there were uniform periods. So for instance, a very evident uniform period was the 20 years from 1999 to 2019 that were dominated by alternative rock. You can see in those years, the network activity was creating pretty uniform activity. But for instance, you can see that there were times where things were changing much more. One case is like between 1926 and 1939, it was actually not possible to create a meaningful cluster because there was just too much of activity. So before we had an era that was more or less dominated by classical music, and then a lot of things happen in the musical industry, and then we have the emergence of a jazz period, then a pop period, then there is the British invasion in 1966 to 1972 with the beat rock dominating the scene. And the nice thing about this label is that you don't need to create a different process to find these labels. So when you do normally this kind of agglomerative clustering, you find a cluster and then you will probably have to look at some sort of like the relative frequency of the various labels in this cluster. But in this case, the cluster was found with network distance, and calculating just the relative frequency of the genres is not the same process, right? So there will be a disconnect if we were to do that. But here, what we can do is say, hey, a period, a cluster here, is nothing more than a node attributes. We can say we are going to count the number of albums that bands put out from 1999 to 2019, and that's a node attribute. And then you can calculate the distance between that node attributes with all the other genres. And you can pick the genre that is the closest to that cluster. And you do it closer using the network distance again. So the process that you use to find the labels for the cluster is the exact same process that you use to find the cluster itself, which is very nice. So here is the labels are not generated by simply the genre popularity in absolute counts, but by calculating the distance between the periods and the genre. So how does this temporal cluster look like? For instance, the cluster dominated by pop that goes from 1946 to 1965 has this kind of pattern of activity. It's concentrated in these left parts of the network where you can see the darker nodes is where most of the activity happens. If you look, for instance, at another cluster, the one from 1973 to 1981, for instance, after the beat invasion, you can see that it's still on the left-hand side. So the dark nodes are still tends to be on the left-hand side. But it's pretty different from the activation pattern of pop. You can see now I'm going to do a back and forth here. You can see that the activity has moved in the network. And in fact, you can, if you put together more of these periods, you can see that this network has a clear left to right temporal evolution that you can see. So these were three applications that I wanted to talk about. Now, the question is, what's next? So I show you fundamentally three techniques. One, it was this network variance that was developed by Renault. And then there is Euclidean distance. And then there is this clustering that you can do. What's next? Well, we can think of more statistical measures that can be extended to use a network logic. Information entropy, cosine similarity. Fundamentally here, the idea is that we need to figure out that this measure works by assuming that all the dimensions of analysis in a sense are equal. And we need to figure out a way to tell this measure, well, not really, because some pairs of these dimensions are actually more related to each other than other pairs. And they are related in this complex structure that is defined by the network. So we need to find a way to plug the network in information entropy, cosine similarity, and whatever other statistical measure that you can think of. You can also build more advanced network analysis techniques. I did data clustering, but you can think of, well, can we actually run a regression on this? Like simple linear regression by its name is a linear regression. It just assumes that there is this linearity and it still works in an Euclidean space. Does it make any sense to give to a linear regression framework a complex space to work with? I actually don't know if the answer is true. Maybe if the answer is yes. Maybe the answer is no. Maybe it doesn't make any sense. But it's an interesting question. It's one that is worth exploring. And then we can find more applications. The thing that I try to communicate with this talk is that we can talk about very diverse things. We talked about political polarization, archaeology, and music. These can be very easily applied to epidemics, to marketing, to whatever process you can run on your network. You can calculate distances between the node attributes that this process generates. So, very quick recap. What I try to convince you today is that node attributes are interesting to study. We do not have to limit our network science study to nodes or to communities or to the networks as a whole, like the grid distributions. We can also look at node attributes, and they are super interesting to study. And I think it's a little bit of an unexplored or not as well explored place to look at. These node attributes represent traces of processes that happen on the network and they are mediated by the structure. So using this network measure is necessary because the network structure is complex and you cannot really approximate it with simple measure. And we can do a bunch of analysis with this. Pairwise distances, concentration, clustering, error detection on networks. Final slide for you. I wanted to put out the 4 papers that I based this talk on about political polarization, archaeology, the clustering, and then the music analysis. And with this, I thank you very much for your attention. And if there are questions, I will be more than happy to take them.
Great. Thanks, Michele. Any questions in the room? Or if you're online, you can raise your hand here. Yeah, Gesina, do you want to ask a question?
Yeah, thanks. I was just trying to figure out how to raise the hand on Zoom. Thank you for a very interesting talk. So I come from the statistical side, and people have been looking at these random dot product graphs where they say the probability of an edge is directly related to the attributes. What do you make of those?
Oh, this is a very interesting question, and it's something that I actually was very interested in exploring. So assuming that I understand the question correctly, one thing that I was thinking was that these kind of techniques can be used to infer a network structure, actually. Because let's suppose that you only have attributes, right? And so you're going to say, well, I think that there is some sort of complex space behind the data generating process of these attributes. And we can say, okay, well, what if I create a bunch of random networks and then I use these distance measures to figure out, well, maybe they can give me an idea of the likelihood of this network being behind the process. Because if I assume that two dimensions should be correlated by this network, then changes in these two dimensions should go together, and therefore an edge will create lower distances, right? So this could be, if I understood your question correctly, could be an interesting way of validating this kind of, okay, uh, uh, can I generate a bunch of random networks and figure out which one is the most likely to be behind the data generating process of these attributes?
Yeah, for example, yes,
Yeah.
another way of using the attributes, or always also going on with the archaeology example. So if you don't have the genetic data, can you still infer relationships of the network?
I believe the answer is yes. Now, it's a little bit more complicated than it probably I'm thinking of, because I did try to do a little bit of this work before, but I quickly realized that if I did things a little bit too naively, and then some very trivial result poured out, in the sense that one way, for instance, of minimizing distances, because this is what I was hinting at, is to just make a random graph. Like a random graph will minimize distances because it will create these shortcuts, right? So just doing this naive approach probably wouldn't work. But I believe that there are smart things that can be done with this, and probably, yes, probably you can reconstruct the genetic information, but it does need a little bit of thought.
Okay.
More thought than I give to this problem, for sure.
It makes sense.
Yeah, Rohit.
Thanks, Michele. Thank you for the talk. I have a sort of a slightly high-level question, perhaps. Is it fair to say that this methodology revolves around trying to find whether node attributes are correlated to whatever process generated the edges?
I will say so. I mean, there are some things that you would assume they are related, but they aren't. Like, for instance, a lot of the time when I talk about this technique, people assume, okay, well, since I show networks like, let's see, yeah, I can't go back now, but yeah, there is this little slide that I have the process, and I show these kind of networks that have communities. People will assume, okay, well, but if I don't have communities, then I can't use these techniques. The answer is actually no. Like, the structure doesn't necessarily need to have these lumps. But to your question instead, I will say yes. Like, if you have a node attributes that has no relationship, like this completely orthogonal to the edge generating process, I think that using the network actually doesn't work at all. And so you will have to figure out something else to do, because if you decouple, the network topology from whatever process generated the node attributes values, then these techniques are not going to be helpful for sure. I actually have something that I'm working right now to do the clustering, the example that I use also in this talk. I created a little bit of a slider that's depending on a parameter that can go from 0 to 1. You use a purely Euclidean distance if it's 0, the parameter, or the purely network distance if it's 1, right? And I can see that there are some cases in which actually turning it to 0 is the best thing, right? Because in that specific case, the network isn't related to the node attributes, and you should just use the normal Euclidean distance or whatever other distance measure you want to use. So yes, the answer is definitely yes. And the interesting thing about actually having this parameter to play with is that it is actually very rarely a straight 0 or a straight 1. It's always somewhere in between, which is something that I think it's interesting, but I need to finish writing the paper first before I actually can properly interpret.
Thank you. Can I ask a quick follow-up?
Yeah.
Some of the networks that we study often, I think also, if I understand correctly, your archaeology example, the edges are also derived not from observing the edges themselves, but from observing correlations between the nodes, right? So somehow here you have two node attributes, or two kinds of node attributes maybe, and you've chosen one of them to make edges, and you're treating the other as node attributes, and then you're defining the variance and so on.
Yes.
How do you make that choice versus just treating them as two distinct groups of attributes and just forgetting the network? I mean, what's the network adding here?
Yes, that's a very fair point. And in fact, this underlies multiple things. Like, for instance, even the music network, in reality, if you really want to look at that, it's a bipartite network where you're connecting artists with bands. And so what I used was a projection of that bipartite network, right?
Yeah.
So the idea here is that there should be some hints. There is this choice is not arbitrary of what you use for edges versus what you use for the actual node attributes themselves. You basically need to try to understand what your data is telling you, like what are the characteristic of this data, and then you can say, okay, well, I think that this specific thing, like these specific attributes, is the channel through which these other attributes may change its values. Like this, the data generating process of these attributes is mediated by these other attributes. This is not necessarily symmetric, right? Because I think I'm more comfortable discussing the music example. Think about it this way. It is much easier to see how two bands should be related because they share members, which is one type of attributes that these bands have, versus they share genres. Because two bands may share genres but not having much to do with each other. For instance, you have two pop bands, but one played in the 1940s and one plays today. The relationship between them probably doesn't help these two bands sharing members. So it would be weird to have a network where the edges are the genres and then the node attributes are the people, because then the people cannot necessarily be shared with the genres. But the other way around, I can see how the process will make sense. This particular drummer or this particular guitar player, they are interested in playing this specific set of genres, and that will create a much immediate relationship between these two bands because the same people play in these two bands, and then will correlate the genres that these two bands will play. I hope this answered your question.
Yeah, thank you.
It actually leads to one question that I had, well, kind of two questions, but also about kind of choices you have to make. So in this case, taking the band example, the genre of a band was static, not changing over time, but we have some high profile examples like, well, not Italian, I guess, but Beyonce changing to country music recently. So like, how can you incorporate like the dynamics of the attributes as well if they change over time? And directly related to that is also like soft clustering instead. So bands can have multiple genres, right? They might fit within multiple, but I don't think that this version can directly handle that. So is that something that is also possible to deal with?
Yeah, okay. So for the first part, I haven't really thought about in those terms yet. So yes, I was looking at genres statically. My first like hunch, like the first thing that I will do will be to say, well, okay, so we have the genre, let's say pop, right? And well, I can always split these single node attributes into multiple node attributes because I could say, okay, well, this is the number of people who, or like number of albums, pop albums that were out in this particular year from these particular bands, right? And so I will have a pop 2022 attributes, a pop 2021 attributes, and so on and so forth. So in that way, you can also say, okay, well, I know that these various node attributes represents a temporal evolution of these specific attributes, and so then I can do something with it. So that's for the temporal evolution. For the soft clustering, it's an interesting question. I think that bands playing different genre is kind of like at the basis of being able to do the genre clusters because basically you say, okay, well, there is the pop genre will distribute on the network in some way, then the rock genre will distribute in the network in some way. The same band can have both, right? Can have some pop album and some rock album, and that will decrease the node attribute distance of these two genres on the network, and therefore I can use that for the clustering. But the clustering itself is not soft clustering, so that's, I don't know if I can make genres being part of multiple clusters at the same time because the same bands play in them. That's an open question that I haven't really given much thought about yet.
Thanks. Any more questions in the room or online? If not, let's thank Michele again.
Thank you.
And yeah, see everyone next week with Yelena. Yeah, great. So yeah, thanks again, Michele.
Thank you. Thank you.
Bye.
Bye.